So today we will be starting some calculations. You will see many formulas today. But let's look in general what we are actually doing in physics. So this is what we would like to study, nature, how nature behaves. We would like to make predictions about the behavior of nature. And in order to do that, we first create a mathematical representation of the model. So I'm sure you are already saying that solve problems in which, okay, if my object is at the position x equal to 5 meters at this and this time, this is your mathematical model. You are creating a model which represents your nature. Those mathematical equations are not nature itself. Well, that's kind of obvious, but it's just a model. And then from your mathematical model, you just make mathematical derivations. You take integrals, derivatives, you multiply them, divide them. And then at the end, you get another model of the nature. It's still not nature. It's just a model which you believe represents nature. So then, okay, so from here, you first write the model of the nature. In mathematical terms, that's our language. You manipulate your mathematical expressions. You get some derivations, some results. But still, you need to interpret your results in terms of the properties of nature. So it might be that you are studying the projectile motion, which we will be doing right now. You say that, okay, at t equal to 0, my object is at 3 meters from the origin. And then you do your mathematical derivation. So your friend is, let's say, 3 meters from the origin, which is here. And then you do the derivation after 5 seconds. And from apparently, he will be still staying there. So in 5 seconds, I predict that he will be still 5 meters from me. So that is my derivation, my result. And my model will be, if I hold my watch and wait for 5 seconds, your friend will still be there. And that will prove that my model is consistent with nature. And here is again where your mathematics courses will enter. They will be important in doing the mathematical derivations. Okay, so this is what our prediction is. This is what we would like to do. We would like to make predictions about nature starting from some initial condition of the nature. Now, in physics, we all do analysis. I personally didn't know what the word analysis meant until like 5 years ago. I always used it. It was analysis. So does anybody know what analysis means?
Analysis means we have a complex subject, making it into parts, and finding the connection between that part. And then by that, having aware of what is going on.
Exactly. So we have a complex problem. This semester we will be studying complex three-dimensional motions. So rather than studying the motion as a whole, we just divide it into smaller parts. And we hope that each one of these smaller parts are easier to solve. And once we solve each one of these smaller parts, we combine the results to obtain the final result and have some prediction about how our nature will behave. So, of course, in general, if you look at any motion, any kind of motion that you see in nature, like this one, was it visible to everybody? Well, it was small, but it has rotation and translations. Translation in that direction. But it could, no, not just in that direction, by the way. It just first made translation in that plane. It went up and then down, hit the ground, and just jumped from there to there and back, made some complicated motion. And, well, that is the whole motion. We would like to divide it in small parts first. So rotation we will be studying in several weeks' time. Let's ignore the rotation for the time being. That will be an approximation. And, well, we know that it moves in various directions. But let's also assume for simplicity, for the time being, just study one-dimensional motion. How do we describe one-dimensional motion? Now, this week we will be mainly interested in just description of the motion. We will be describing motion, and next week or the week before we will start what causes and what changes the motion. So this is my I will assume that my object moves along this line. I have to specify the position of my object. I should say that my object is here, but I cannot, I mean, on a paper, when you are working on the paper, you cannot just point, okay, my object is there. That doesn't really work. So we have to find a mathematical means to represent it. So I first choose an origin. Where should I choose the origin? Somebody else, not you always. Is there a reason why I chose it there? Who says yes? No, there's no reason. I mean, come on, some answers, some feedback. I could have chosen the origin there or there, equal. I don't really care. But you have to be careful though. If I choose the origin here, and then put some object over there, so just knowing this distance from the origin, well, this is a large object, so to specify the position, I have to fix some point on the object. I will choose this left side. Well, it's a regular shape, so I will choose the left side. So if I know the distance of the left side of this object from the origin, then I know the position of this object completely. That completely specifies the state of my system. If your friend comes and chooses the origin over here, he will say that, no, this point is not 3 meters from the origin. He will say that this is the origin. That point is minus 2 meters from the origin. Well, here I chose a positive sense, by the way. I said that this is my origin, and this is the positive sense. So if you have another origin here, then this object will be, in the negative sense, 2 meters from that origin. So I will say that it is 3 meters. My friend will say, no, it's minus 2 meters. So the plus 3 meters and minus 2 meters are obviously different things, but be careful. If you go back to this sketch, I am first making a mathematical representation. My representation of the system and my friend's representation of the system are different, and this difference I have to take into account when I'm interpreting my results. I will say that the object is 3 meters from the origin plus 3 meters from the origin, which will denote this point over here. He will say that my object is minus 2 meters from the origin, and it will still be here. Although we are saying that it is different numbers for the distance from our origins, when we interpret our results, we both agree that the object is over here. So if the choice of the origin, arbitrary, nature doesn't care about that. But once you choose an origin, write your mathematical representation, do your manipulations, and obtain some prediction about the nature, in interpreting your result, you have to take into account your definition of origin. Question? Questions? If you have any question, just interrupt me. Most of my students complain that, well, when I use the blackboard, I'm writing so fast on the blackboard that they cannot copy on their papers. But now I'm not using blackboard, I'm even talking fast. So if you want me to slow down, ask questions. Any questions? Okay, this was the positive sense. If my block was there, suppose my block is moving. At some TI, I measured its position. It is at plus 3 centimeters. At some other final time, it is at minus 1 centimeters. Okay, just again remember, once I choose my object, I have to be consistent on how I measure the distance. Here I'm measuring the distance from the left, from a point on the left face of this rectangle. I should use the same point at all times to specify its position. If I choose this point to specify the distance from the origin at this time, and this point to specify the position at this time, then I will be doing wrong. So my object moves from plus 3 centimeter to minus 1 centimeter. Then I can define the displacement. It's the final position minus the initial position. This is my displacement. So I have the 3 centimeters minus 1 centimeter. that is 4 centimeters. That is my displacement. Right? Somebody else first. Yes, one answer is correct. Your answer, yes or no? Who says yes? Who says no? So we are only 10 people here? So I said, okay, delta x is the final position minus the initial position. So final position is 3 centimeters, initial position is minus 1 centimeter, so the displacement of my object is 4 centimeters. It is plus 4 centimeters, so it is displaced in the positive direction. So the displacement is from plus 3 to minus 1, so the displacement is minus 4 centimeters. The final point is minus 1 centimeter. The initial point is 3 centimeters. So this is wrong. Well, I should confess, I didn't do this on purpose. I should correct in my slides. But it just brings me a good idea that I should implement more mistakes in my slides to keep you awake. You should be shouting at me saying that this was wrong. Okay, so I know the displacement. Then the average velocity. Well, velocity, what we want to measure is how fast the object is moving, how fast it is changing its position. So an interesting quantity would be the amount, the amount of change itself doesn't really tell me how fast the object is changing, because if I consider a slowly moving object, its position will be changing slowly, but if I wait long enough, it will be displaced a larger distance. So I don't really want this is not really a measure of how fast the object is changing its position, but the average velocity, it is the displacement per unit time, is what determines how fast my object is moving. Okay, just a note about the Greek letters that we will be using. This is capital, it's called delta. The capital delta is usually, not all the time, but usually denoted by differences, finite differences. They can be small, they can be large, there's no restriction on them. I have this letter, which is the small delta, which is finite differences. They are not zero, but they are small. Now, whenever you see this delta, you are talking about some quantity that is changing with some other parameter, and that change is small, but still finite. And then we use a d, that is infinitesimal changes. That is a change that is smaller than any number you can think of. That's how we define these small. Of course, these are just conventions. They are used most of the time, not always, but most of the time these are used. So let's just assume that this is the position versus time graph of my object. So at some time here, at 1 second, it is at 0.1 meters. It reaches the point A. Then at the time 4 seconds, it reaches the point 3.2 meters. So if I want to calculate the average velocity, okay, delta x will be the displacement in x. It moves from here to here. So this is my delta x. Well, the reason why I put the absolute value here is, remember, delta x has a sign. It can be both positive and negative. The length of this the side of this triangle, this right triangle, is always positive. So this length determines the absolute value of delta x. So if, in this case, delta x itself is positive, so the absolute value of delta x will be equal to delta x. So delta x is just this length. Delta t is this length over here. It is 3 seconds, and delta x is 3 meters. And remember the notations. Note the notation. This is 3.2 meters. I am claiming that the measurement is precise up to 0.1 meter. It's not more precise. It's not less precise. The uncertainty here is not 1 meter. It is neither 1 millimeter. It is 3.2 meters plus minus 0.1 meter. And the time measurement is, here I'm claiming that the error in the second is 0.1 seconds. This is the significant figures. This one, I'm sure, this 0 can be off by 1. It can be 0.9 seconds or 1.1 second. The same holds for this 4.0. Well, the average velocity is the final time. Okay, here I got it right. So this is the final time. This is the initial time, the initial position, divided by the final time, the initial time. So this is the distance it covered in this amount of time. So its velocity is 1 meters per second. This is the unit of velocity, meters per second. The uncertainty here is again 0.1 meters per second. I'm not claiming to have a knowledge of the average velocity more precise than 0.1 meters per second. Since I don't know the precise position better than 0.1 meter, I cannot measure the velocity more precise than 0.1 meters per second. This is the average velocity as my object moves from the point A to the point B. Of course, if you look at the graph, so you see, if I would just divide these time intervals into equal time segments, you would notice that first it is very slow. It's just moving slowly, and then it is accelerating. So we all have the feeling that, okay, this is the average, but I know that as my particle moves, at some points it will be slower, at other points it will be faster than this average velocity. So that brings us to the definition of instantaneous velocity. By the way, this is nothing but tangent of this angle over here. It's this divided by this. Of course, if I want to define the average velocity as the tangent of an angle, I also need to give a sign to the angle. And usually the signs are such that this is your horizontal axis. If you go counterclockwise, the sign is positive. So in this sketch at least, the angle alpha is positive, the velocity is positive. If you go from this axis to the clockwise sense, then you are going to negative values of angle. So now the instantaneous velocity, we just said that in this diagram, in this special case, my object first moves slowly. It covers less. Well, if you look at the average velocity between this point and this point, it is smaller than the average velocity between this point and this point, because the angle here is much larger than the angle here. I can define the instantaneous velocity as the angle that the tangent line makes at a given instant. So I take this point B, I bring it closer and closer and closer to the point A. So that in that case, I calculate average velocity in a very small amount of time. But in a very small amount of time, the velocity of my object doesn't really change much. So for that very, very small amount of time, the average velocity will be equal to the instantaneous velocity. If I take that time integral to be infinitesimally small, then I will have an exact expression for the instantaneous velocity. So if I take the point B to the A, the average velocity between the time A and B, or I can also write as the limit as the final time approaches the initial time. Okay, remember, at initial time I make a measurement of my particle, the position of my particle. At final time, I make another measurement of the position, and I see how much my particle changes in that amount of time. So if I take the final second measurement to be as close as possible to the initial measurement, I will be able to obtain the instantaneous velocity. I can write it explicitly like this. Well, these differences over here in that limit, as the final time approaches the initial time, the final position, well, since I'm just letting the system move for a very small amount of time, the system will move a very small amount of distance. So both of these will be infinitesimally small in that limit, so I write it as dx by dt. So if I know the position as a function of time, this is in fact nothing but the derivative of that function of time as a function of, with respect to time. So the instantaneous velocity at a given point is nothing but the derivative of the position of my object with respect to time. Do you know who invented calculus? Yes, Newton is one of the inventors of calculus. And this is how he invented it. Leibniz is the other one. There are two inventors. One is Newton, the other one Leibniz. Leibniz, I don't think he was a physicist, though. Newton was a physicist. So he was studying the motion of objects, and he needed some mathematics which didn't exist. So he had to invent his own mathematics. He wanted to study motion. He needed it. He needed it, so he invented it. Well, that's quite common, what physicists do, by the way. We invent some new language. First, the mathematicians complain that it doesn't make sense, it is not consistent, and it's not formal. And after like 10, 15 years, they make formal definitions, and they accept it as a valid mathematical tool. But if you look at this expression, I can just say the change in x in a very small amount of time is nothing but v times that time interval. So if I know the position of my object at a given time, and if I know the velocity of my object at the same time, then I can calculate its position at the successive time. So suppose I have an object here. I know that it's moving in that direction at this instant. I know that if I just look at my object, just 0.1 seconds later, it will be moving, it will be just here. It has just moved a very small distance along the direction of v. So the final position of my object will be the initial position plus v times the time difference, delta t. So how can we use this knowledge to obtain the position of an object at an arbitrary time if we know the initial position x0, and also we know the velocity for all times between the initial time and the final time? So how can we determine its position? Well, I know how my particle moves in infinitesimal increments. This is what the previous expression told me. If you look at here, if I know the position at some time and the velocity at that time, I can find its position at a very small time later. I can do the same trick successively, many times. So at some time t, my object is here at ti, it's at xti. Then it moves in a time delta t, it changes its position, it displaces itself by this amount. So it reaches this point ti plus delta t. Then at the successive instant from xti plus delta t, it reaches its position at ti plus 2 delta t. And then in the next step, 3 delta t, 4 delta t, step by step, it will be moving from the initial position to the final position. At each one of these steps, the displacement is nothing but the velocity within that time interval times the length of that time interval. So this will be its displacement in this time interval delta t. This is how we define the velocity. Well, you can ask, okay, so between ti plus 2 delta t and ti plus 3 delta t, its velocity is changing all the time. So why did I use the velocity at ti plus 2 delta t? Any ideas? Remember, delta t is very small. In a very small amount of time, the velocity doesn't really change at all. So I could have as well written here, instead of ti plus 2 delta t, I could have used ti plus 3 delta t, or any velocity in that time interval, I could have used it. They will be all valid. If I get a different result, whether I use ti plus 2 delta t or ti plus 3 delta t, then it is not physical. I shouldn't get the different answer. I should get the same answer. But in your calculus courses, when you study these integrals in more detail, you will see that if these two cases give you different results at the end, then the integral doesn't exist. But in physics, the functions we have are always nicely behaved. So the limits always exist, the derivatives always exist, integrals always exist. Well, I can do this step-by-step evolution of the position of my particle until I reach the final time, each by very small steps. Well, if I sum everything up, if you look at here, I have the position at time ti plus delta t with a plus sign. I have the same thing with a minus sign. The same thing happens here. I have the position at ti plus 2 delta t with a plus sign, and I have the same with a minus sign. So when I sum everything up, this will cancel this one, this will cancel this one, this will cancel the next equation over here, which I didn't write. This will be canceled by the previous expression. So what will be left is, this will not be canceled, xti, but xti is just x0. So it has a minus sign, minus x0. And this will not be canceled. So I have the position at my final time minus the position of at my initial time is equal to this sum, k from 0 to n minus 1, v times delta t. Well, v times delta t is the very small increment in the position of my object. So here what I'm doing is, the total what this equation tells me is that the total displacement of my object is nothing but the sum of very small displacement at each time interval. Of course, this is just an approximation as long as you keep delta t very small. You have to take the limit that delta t goes to 0. And of course, if in that limit you will be having infinitely many terms here. And that limit is what we call the integral of a function. Yeah. Integral is in fact nothing but a fancy summation. You are summing infinitesimally small quantities, very small quantities, but you have infinitely many of them, so you get a final answer for the integral. This just tells me that v dt is nothing but the very small displacement of my object within this time dt. Here I'm just summing all these very small displacements starting from the initial time up to the final time. Well, how do I determine these limits? Well, if you look at the first expression over here, my time in this sum, my time starts from ti, so that is my limit over here. And it ends at ti plus n minus 1 delta t, this expression. But that is ti plus n delta t is the final time. So this is just delta t before the final time. But since I'm taking delta t to 0, this final term in this summation has the time t final. So here, by summing over k equal to 0 to n minus 1, I'm in fact summing over times from t initial up to t final minus delta t. And when I take this limit delta t, I just obtain an integral where these limits are determined by these sums over here. Yes? I wrote it wrong. It has to be ti. So you are learning to object. Good. Well, we can study a special case if we have motion with constant velocity v0. Well, we already know what the answer is. If an object is moving at a constant velocity v0, the average velocity is v0. From the definition of the average velocity, we could have obtained the position at any time just using the definition of the constant velocity. But let's just see how we obtain it from this summation or integration thing. This is our previous result. The total displacement of my object from time x0 to the final time is nothing but the sum of the displacement from each very small steps. Well, this sum is nothing but if I want to go from here to there, what I need to do is I need to take steps. And well, my total displacement will be nothing but the total steps that I have taken. So it is this sum. At the end, the only difference is that I'm taking very small steps rather than taking such large steps. I'm just taking very small ones, but infinitely many of them. So I get an integral. Okay, let's come back here. Motion with constant velocity. Well, this velocity is the same, so it's just v0. Well, if you have such a sum, a constant factor over here, I can factorize it. I can take it out of the summation. This is nothing but, if I take it out, I will end up having the sum of delta t, which is 0 from 0 to n minus 1. I have n minus 1. I have n terms over there. N terms, each one equal to delta t. So v0 times n times delta t. But n times delta t, well, n is the total number of steps I took. Delta t is the time difference in each one of my steps. So n times delta t is nothing but the total time difference. So I end up having v0 times the time difference. So the displacement is nothing but my constant velocity times the time difference. And this is, well, delta x over delta t has to be v0. If you just move, well, this expression is nothing but delta x is over here. This is delta t, this is v0. If you just move it over here, this is nothing but the definition of the average velocity. So we have the motion, the position of the object. We describe the changes in the position of the object. And the changes in the position of the object, the rate of change of the position of the object, we define what we call the velocity. But velocity of objects is also changing, so that is what we call the acceleration. Well, the steps are identical. If I have an object that is moving, that has a changing velocity, I can talk about the change in its velocity. It has an initial velocity, the final velocity. So the change in the velocity will be just final velocity minus the initial velocity. In a given amount of time, in a time delta t, so the average acceleration will be just the change in the velocity divided by the total time in which that change in the velocity has occurred. I can just take the limit as this delta t goes to 0. And in that case, I define the instantaneous acceleration. And this is nothing but if I know the acceleration, well, this gives me, if I know the velocity, I can calculate the acceleration from the velocity. And this tells me how I can calculate the velocity given the acceleration. Again, remember, acceleration is the rate of change of velocity. If at some time t0 I have the velocity vt0, and I'm interested in the velocity at a later time, what I need to do to find the change in the velocity is just to add up all the small changes in the velocity. So a times dt is a very small change in the velocity at time t prime. So I sum all of them up to obtain the velocity at the time t. Okay, acceleration and the direction of velocity, they do not need to be the same. The direction of velocity and acceleration doesn't have to have anything in common. This will be especially important when we study motion in more than one dimension. But in this case, for example, if I'm moving in that direction, let's say I'm making a one-dimensional motion in that direction, I will be moving there. Then my positive direction is over there also. So I'm moving in the positive direction. Now I have 0 velocity. I'm moving. My velocity is now positive. That means the change in my velocity was positive. This is positive. This is positive. So the average acceleration was positive. As I go from here, then start moving up to here, the average acceleration is positive. Then if I continue moving, and at some point I decide to stop, I stop. All this time I have been moving in the positive direction. But initially, I had 0 velocity. Then I had positive velocity, so I had positive acceleration. Then I had 0 velocity, so from positive velocity to 0, my velocity decreased, I have decelerated, I have negative acceleration. So although I was moving in this direction, acceleration was in that direction, in the negative direction. Now I turn around, So I start moving again. My acceleration is negative. I am accelerating, I am going faster, but my acceleration is negative. Then I stop. My acceleration was positive during this process because my velocity changed in that direction, in the positive direction. So the acceleration was positive, but I slowed down and stopped. So positive acceleration doesn't mean that you are increasing your speed. It depends on the direction of your velocity.